Transport Phenomena in Biosystem, Module 10, Shell Energy Balances and Temperature Distributions, Segment 2, Heat Conduction with an Electrical Heat Source. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about shell energy balances. In this segment, we will discuss about heat conduction with an electrical heat source. Let's consider an electric wire of circular cross-section with radius r and electrical conductivity Ke. Through this wire, there is an electric current with current density I. The transmission of electric current is an irreversible process, and some electrical energy is converted into heat. The rate of heat production per unit volume is given by equation 10.3. The quantity as E is the heat source resulting from electrical dissipation. We assume here that the temperature rise in the wire is not so large that the temperature dependence of either the thermal or electrical conductivity need to be considered. The surface of the wire is maintained at temperature T0, and we will focus on how to find the radial temperature distribution within the wire. Let's consider an electrically heated wire as shown in the right figure with a cylindrical shell of thickness delta R and length L. Since V equals to 0 in this system, the only contributions to the energy balance are shown in equation 10.4 to equation 10.6. Note that in and out is taken to be in the positive R direction. We now substitute equation 10.4 to equation 10.6 into the energy balance. Division by 2 pi L delta R and taking the limit as delta R goes to 0 gives equation 10.7. The expression on the left side is the first derivative of RQ with respect to R to yield equation 10.8. Equation 10.8 is the first order differential equation for the energy flux, and it may be integrated to give equation 10.9. The integration constant C must be 0 because of the boundary conditions that at R equals to 0, QR is not infinite. Hence, the final expression for the heat flux distribution can be expressed by equation 10.10. This states that the heat flux increases linearly with R. We now substitute Fur's law into equation 10.10 to obtain equation 10.11. When K is assumed to be constant, the first order differential equation can be integrated to give equation 10.12. The integration constant is determined from the boundary condition that at R equals to R, T equals to T0. Hence, C2 equals to SER squared per 4K plus T0, and equation 1012 becomes equation 1013. Equation 1013 gives the temperature rise as a parabolic function of the distance R from the wire axis. Once the temperature and heat flux distributions are known, various information about the system may be obtained. The maximum temperature rise may be calculated using equation 1014, whereas the average temperature rise may be calculated using equation 1015. Thus, the temperature rise average of the cross-section is half the maximum temperature rise. Heat outflow at the surface may be calculated using equation 1016. There are many examples of heat conduction problems in the electrical industry. The minimizing of temperature rise in click-side electrical machinery prolongs the installation life. For the next segment, we will discuss about forced convection. Until then, I am Yusuf from Institut Teknologi Bandung.